Yes. Good idea.
Buenos días, damas y caballeros.
Speaker online.
Okay.
So today our North Atlantic seminar has become South Pacific because the speaker is in Sydney, Australia, and we are in Santiago de Chile. So it's truly South Pacific rather than North Atlantic seminar. But the geography doesn't matter, mathematics matters. So our speaker is TOMASZ MASZCZYK, one of the co-organizers of the seminar, and today he will treat us to the Leavitt path algebras of nothing less than quantum quivers. Tomek, the floor is yours, the Zoom is yours, take it away.
Thank you, Piotr, for this nice introduction. So I'm going to speak about Leavitt path algebras of quantum quivers. The plan is following. My plan today is to break the spell of weirdness of the labyrinth of quantum theory. So first, I will introduce the categorical notion of quantum sets. Then I will pass to quantum quivers and their algebraic invariants. And our Ariadnist thread will be category theory. So let me start from elementary facts about the category of sets. First of all, this category is symmetric monoidal with respect to the Cartesian product as a monoidal product, and the singleton as a monoidal unit. Inside this category, every object, every set, has a unique co-commutative comonoid structure under the diagonal map from S to S cross S as a co-multiplication, and the constant map from S to this singleton as a co-unit. Moreover, if you have an additional structure on this set of algebraic nature, like a bimonoid, okay, like a monoid, then it becomes in a natural manner a co-commutative bimonoid, which means that the multiplication and unit maps are automatically comonoid maps. So the next step is linearization. Having this set theoretical structure, we can regard sets as bases of vector spaces. And then, after linearization of the comonoid structure, this space spanned by this set becomes a co-commutative coalgebra. Similarly, if we linearize the bimonoid structure, this vector space becomes a co-commutative bialgebra. And now, the forgetting co-commutativity, or in the dual situation of algebras, commutativity, is an allegory of quantization.
Tomek, a question.
Just because
yes,
we have few, and I want to understand everything. Can you recall me the definition of monoid?
Monoid is a set which is equipped with an associative product, multiplication, okay, which is unital with respect to some unit.
Okay.
That's all.
Perfect.
For instance, every group is a monoid. Endomorphisms of a vector space, it's a monoid.
Just a very basic structure.
Yeah.
So this coalgebra structure, which is co-commutative, induces on these objects the structure of a co-commutative coalgebra. And if we start with a monoid, then after linearization, it becomes a co-commutative bialgebra. Bialgebra is an algebraic structure which is a coalgebra and algebra at the same time. And these two structures are compatible in an obvious manner. So now, let me formulate the following allegory of quantization. Usually it's based on the passage from objects which are coalgebras or algebras, and we are forgetting about this co-commutativity or commutativity. So the question arises, is this sufficient for quantum theory? It turns out that by far it is not. To speak about quantum theory in mathematical language, we need a more fundamental tools, some formalization, which is based on category theory. So now I'm going to pass to some more advanced notions from category theory, but you should be sure that it is not something very complicated. In fact, these are basic categorical structure you used for all your mathematical life. Even maybe you were not conscious about this fact. So first, such a basic structure for doing mathematics, or even speaking mathematical language, is the notion of an elementary topos. It is a category which is equipped with finite limits, in particular a terminal object and pullbacks. And it is Cartesian closed, which means that this product has a right adjoint, which is denoted by this exponential symbol. If you have two objects, x and y, then you have some object of mappings, let's say, of mappings from the object x to the object y.
And so, Tomek, just a stupid question. Tomek, wait, just a stupid question. When you say mappings, you mean what? Like morphisms in this category, or what?
No. It's an object. It's an object which is a generalization of a set of mappings between two sets.
Okay, but what plays the role of these mappings?
It's a formal construction. It's a right adjoint to the functor of taking the Cartesian of a product, with an object x.
Mm-hmm. Okay.
For instance, there are many examples of this. For instance, if you have topological spaces, then you can give on the set of mappings from x to y, you can define a topology.
But this would be a set of all continuous mappings, right?
In the category of the category of topological spaces, we consider morphisms which are continuous maps.
Yeah, that's why I asked my question. Yes, but these mappings are actually morphisms in your category.
No, Piotr, I think that you are confusing
the object,
two different things.
The exponential object is something different. It's a new topological space.
I know that there's a new topological space. That's clear to me that there's a new topological space. But I'm all the time questioning what one means by mappings. We are not talking set theory. We are talking some objects in a category. So my first reflection would be, well, these mappings should be some kind of morphisms.
No, mappings are only in examples, but in general, in abstract theory, it's just an object.
Okay, but I know. Okay, yeah. This is what Tomek said. This object which is given by an adjoint. I understand it. Yes, but in this particular example, where you had the category of topological spaces, okay. And I know that the space of mappings can be equipped with some, compact open topology, whatnot.
Yes.
But I'm still curious whether this abstract categorical construction in this particular setting of, say, topological spaces would yield all continuous mappings.
Yes.
That's what I was saying. So I didn't confuse anything. Sorry. Okay, let's go on.
So the next property of this elementary topos is some universal monomorphism, which consists, first of all, of an object omega together with a monomorphism denoted by T from the terminal object 1 to this object omega, such that every monomorphism from A to X is a pullback of this universal one, which means that the diagram below is a Cartesian square. Okay, it's a fiber product. Okay, so there are some examples. So first of all, the category of sets is an elementary topos. And in this elementary topos, this classifier of subobjects is very simple. It's a set consisting of two elements. You can think about them as 0 and 1. And then this universal construction boils down to the characteristic function defining a subset. Okay? As all elementary topos, topos of sets is equipped with something which is called the internal logic. In this way, this internal logic is the classical logic, and Boolean algebras are modeling propositional calculus. In general, the internal logic of an elementary topos is something which is called the intuitionistic logic, where the Boolean algebras modeling propositional calculus are replaced by so-called hating algebras. So now we are ready to formulate the definition of the category of quantum sets. Before, I forgot to say, we have some more complicated examples of elementary toposes being presheaves, which means contravariant functors from the category to the category of sets. If our category C is a locally small category, then category of presheaves is always an elementary topos. Locally small means that morphisms in our category form sets. Morphism between any two objects in this category.
I have a question.
Yes, please.
Do you encounter any natural example of category which is not locally small?
Of course, there are many so-called large categories where even morphism between objects form a proper class. So,
could you give some example of something natural, something which you encounter in ordinary mathematics, not dwelling deeply into category theory?
Of course, it's category theory. So, but examples come from everyday mathematics. For instance,
but not being locally small, TOMASZ. Not being locally small.
Even not being locally small, you can have objects bigger than small categories, for instance, and then functors between them usually do not form a set. Okay. So one level up, you are losing this local smallness in a very easy way.
But the problem is that in the example which you gave,
no,
objects are also not a set. In particular, they are not set. Yes, sets.
What are not sets?
So I would be interested in
morphisms do not form sets.
TOMASZ, so again, let me repeat very carefully. I would be interested in some natural example of category,
yes,
which is the following. I have objects which are set with some additional structure, and then this.
No. You don't have this.
Okay.
If these are concrete categories, then always concrete category means that your objects are sets with some structure.
Mm-hmm.
And morphisms are mappings between these sets, preserving this structure. Yeah. Then always you obtain a locally small category.
Okay. Yeah.
But it's not so big class of categories being concrete.
Okay,
so typically categories are not concrete.
Okay, so maybe it would be my last attempt. Let me reformulate my question. So I would be interested in something which is a natural example. Objects are sets, but there is some reason to requiring that the set, that the morphism between two given objects would be something larger than the set, some subset of mappings. Do you know any such example?
Yes, you can take the category of sets and morphisms being, for instance, correspondences, not being relations. The spans, okay?
Okay, but not being locally small. I would be also interested in.
It is not locally small. If they are not relations, the resulting category is not locally small.
And just to make sure we're on the same page, locally small means that for any pair of objects, the morphisms do not form a set, right?
Not being locally
So
small.
not locally, yes. Locally small means that you have home set.
Exactly. Okay. Then the morphisms are sets. Okay. Good. Just double check.
Okay.
So now we are ready for a definition. So to guarantee that our quantum sets form a topos, as before, the easiest way to achieve this is construct this category of quantum sets to be a topos of presheaves. And as the category on which we take this category of presheaves will be any full monoidal subcategory C of the symmetric monoidal category of coalgebras over a field, fixed field K. And then with the tensor product in this monoidal category will be the tensor product of coalgebras, and one-dimensional coalgebra K is a monoidal unit. So this is the formal definition. Okay? And then this category of quantum sets, first of all, is also a symmetric monoidal category with respect to an argument-wise product, Cartesian product of values of this argument-wise values of these functors as a monoidal product, and the singleton constant presheaf is a monoidal unit here. Okay? Coalgebras of dimension 0 and 1 represent presheaves which are the initial and the terminal objects of quantum sets, respectively. Moreover, these two objects, this initial, one is monoidal absorbing, and the terminal plays a role of a monoidal unit in this monoidal structure. And since they are defined by linearizations of classical empty set and the singleton, we still will be calling them quantum empty set and the quantum singleton. And we will be denoting them as empty set and a singleton, respectively. Okay. What about quantum logic? In this category, the internal quantum logic will be called quantum language and quantum logic, respectively. Inside of this category, as in every category of presheaves, there is a class of objects which are called representable. Representable means that this presheaf is a presheaf whose values are given by morphisms in this category to this object representing this presheaf. And the resulting application associating with every object in this category, the presheaf of homes from any other object to this object is called the Yoneda embedding. It's a theorem by Yoneda that due to the Yoneda that in such a way we obtain an embedding of the category C into the category of presheaves whose image is the full subcategory of representable presheaves. Okay, so now we are going to treat this category, the objects of this category and the structure of this category in its totality, on par with what we know about the category of sets. For every quantum set, in particular, we can define a category of quantum elements. By definition, they are pairs consisting of a coalgebra in the subcategory C and an element of the value of this presheaf on this coalgebra C. Morphisms between such pairs are coalgebra maps which are compatible with these mappings, set theoretical mappings between these sets of points, and composition of such pairs is obvious. Now, we can observe that the category of coalgebras is very similar to the category of sets themselves. First of all, we have something which could be called the fundamental theorem of coalgebras, okay? Which says that every coalgebra is a filtered colimit of finite dimensional coalgebras. It's a kind of hierarchy which we know from sets. We know that every set is a filtered colimit of its finite subsets. For instance, singletons, okay, of elements contained in a given set.
Sorry, Tomasz, filtered
another
colimit.
fact.
May I have a question?
Yes.
So in this context of ordinary set theory, should I think about this filtered colimit as just not disjoint
In this
sum?
context, in this context, unions suffice.
Okay, theoretical unions. Okay.
From the point of the role of finite subset among all other sets, we can look at finite dimensional coalgebras among all coalgebras. And then we see that in a similar manner as finite subsets among all sets, finite dimensional coalgebras form a small subcategory of compact objects. There are objects such that put in the contravariant slot of home, they commute with colimits. Okay? In the covariant, they commute with colimits. Finally, the density theorem, saying that every presheaf on a small category is a colimit of representable ones. All these facts and theorems altogether can be summarized to what, in this context, should be a replacement of this extensionality principle in set theorem. Therefore, we call it a quantum extensionality principle. So this is the first analogy that these quantum sets are similar to usual sets from this perspective. Okay. Although this definition is quite abstract, I assure you that you've seen quantum elements in classical mathematics everywhere. For instance, if S is a singleton, we can recover the set T as the set of its classical elements, which means that Yoneda embedding applied to the linearization of this set T and then evaluated on a one-dimensional coalgebra recovers this set T again. For instance, if T is an empty set, then in this way we obtain the image of the Yoneda of the linearization of the empty set as an initial object in quantum sets, which is this quantum empty set. And the same for a singleton. This time we obtain the terminal object in quantum sets, which we call the quantum singleton. Okay. Another example of quantum elements comes from the theory of coalgebras. If we have a coalgebra, then the group-like element is an element which under multiplication goes to its tensor square. And then if we take the linearization of a set, okay, with its standard algebra structure, then taking S a singleton, we obtain that evaluation of the image of the Yoneda embedding on this coalgebra D on this one-dimensional coalgebra, the linearization of the singleton, recovers these group-like elements of the coalgebra D. So this set of group-like elements of the coalgebra D is simply the set of quantum elements of this coalgebra coming from evaluation on singleton. So this makes this situation very similar to the situation of sets. And such quantum elements coming by evaluation on this one-dimensional coalgebra are called classical elements of quantum sets. Therefore, we can say that classical elements of a quantum representable set is tantamount to group-like elements of this representing coalgebra. Another example of a coalgebra which doesn't come from set theory, but is very interesting because it appears in differential geometry and in algebraic geometry. It's a universal tangent vector. It's a coalgebra which is spanned by two elements. One element is the universal point of tangency, and another element is this tangent vector. The coalgebra structure is, as you see, it is given here, okay? And we see that this coalgebra is equipped with a canonical injective coalgebra map from the one-dimensional coalgebra with corresponding to the singleton, okay, to this coalgebra, which induces a subjective map on quantum elements. Okay? So if we evaluate the image of the Yoneda embedding on this coalgebra D and evaluate this on this coalgebra spanned by this singleton and the universal tangent vector, then we have a surjection onto the set of classical elements of this representable quantum set. And you probably have seen this, because this projection coincides with the canonical projection from the set of G primitive elements in this coalgebra D, where G goes through the set of all group-like elements of this coalgebra D, to group-like elements, okay? Where the definition is given below, how to define this set of group-like primitives, elements for a given group-like element G. And in particular, this construction is well known in the situation of Lie algebras and groups. For instance, to apply this to the coalgebra spanned by the group, we recover the group itself as a set of classical points of the quantum set, which is represented by the linearization of this group. This linearization of this group, since the group is a monoid, it's something which could be called some quantum monoid. Okay, in fact, it's a kind of quantum group. So classical elements of this quantum group form this classical group itself. The same construction you can apply to the enveloping algebra of a Lie algebra. This enveloping algebra is also a coalgebra. It represents some quantum set, and quantum points got by evaluation on this universal tangent vector recovers the algebra, Lie algebra again. Okay?
Rem, I have a question.
So this, yes,
Your Lie algebra is over which field?
any field.
Any field, but the same field as this K, or?
Yes, it can. Yes, it could be K. It could be a subfield of K.
Okay, but could it be something
No.
totally unrelated to this K or not?
Totally unrelated. No.
Okay.
So let's fix this field K once for all.
Okay.
You can think that always there are complex numbers.
Okay.
Okay. Another example of quantum elements comes from the class of categories, which are called categories of finite decomposition, or with finite decomposition property, or denoted by FD in short. Okay, if we have such a category with this property, then linearization of this of morphisms of this category is a coalgebra, when co-multiplication and the co-unit are given as follows. And then we have the following theorems. The first theorem, structural theorem of special kind of these quantum sets. For every small category with finite decomposition property and coalgebra DS above, quantum C points of this quantum set represented by this coalgebra D can be characterized as a set of functors of finite support, which add up when we go along all objects of this category D to 1. Okay. In this definition of the right-hand side of this equality, on the right-hand side we are regarding this f of C as the dual convolution algebra
C-star algebra
of the coalgebra C. No, dual convolution algebra of this coalgebra C. But it's C star is an algebra, but it's not a C star algebra. Okay, where in this algebra the only structure which plays a role on the right hand side is this multiplicative dual convolution monoid with 0. So we forget a little bit of the structure. And then, since every monoid is a category, then this application X makes perfect sense as a function. And then, after this vertical line, we have properties of this function. In particular, if you have a discrete category, in this way you obtain a complete system of orthogonal idempotents, which are very important in quantum logic. We have at least 3 most important examples of such categories of finite decomposition. So first is the monoid of...
Tomek.
Yeah.
Sorry, let me, because I begin to worry. You used up well more than 1/3 of your talk, and according to your own bars, you didn't go even through a quarter. So what we really would like to go is quantum quivers, so you can expedite this prose and go into the poetry.
Okay, so these are examples. Okay, if you have good grasp of these definitions, maybe you don't need these examples. But okay, so I will only show you. If you are interested in details, the notes, these slides will be available. So
will be online, yes.
You can calibrate your intuitions if you are understanding, to check your understanding of the definitions. Okay. Okay, but one category is very important. It's a pair category, which produces in the above way produces the comatrix coalgebra. Okay, it's a structure of linearization of this category, and the category, the quantum set of C points of this corresponding quantum set is the system of matrix units, which are very important in non-commutative geometry. Okay. Another example coming from classical mathematics, which is also important, is the set of representations of the group G on a vector space V. If we feed up the image of this Yoneda embedding by this comatrix coalgebra V star tensor V, then we recover this set of representations of the group G on the vector space V. Okay. So what is the situation between these sets and quantum sets? So we have these two monoidal categories, one category of coalgebras and one category of presheaves. Both are symmetric monoidal, and the natural question arises how the Yoneda embedding interacts with these monoidal structures. And to answer this question, we need the following notion of a partial monoid, generalized and adapted to our categorical context. Original notion comes from Sega. So the definition is like this. Full subcategory of the category of quantum sets is called partial monoidal if contains a monoidal unit, and for any two objects, x1 and x2 of x, in this subcategory, there is a sub-presheaf denoted by x1 cross x2 over x, calligraphic x, such for any three objects in this category, the following obvious conditions must be fulfilled. These are prerequisites for associativity of this tensor product in this model category. And then, if you have this monoidal structure, we expect the following equality, allowing us to avoiding parenthesizing, as in the usual monoidal categories. Okay. Moreover, the monoidal units must act with respect to this partial kind of tensor product as identities. Okay. And then we have the first theorem, that the essential image of the Yoneda embedding of representable quantum sets as partial monoidal symmetric category of quantum sets is defined by the following very nice formula. This formula says that if we have a pair of coalgebra maps from C to D, okay, then they are compatible if the following identity is fulfilled. And then we have the following corollary. Then this Yoneda embedding admits a structure of a symmetric partial monoidal functor, which means that it respects the monoidal unit. This is the meaning of the first isomorph or equivalence. And for category of partial of the image, the category X being the image of this Yoneda embedding, a partial binatural transformation like this, which locally is defined by the formula below, is a binatural transformation. Okay, satisfying axioms of symmetric partial monoidal functor. Okay. Moreover, not only these two structures between in sets, monoidal structure in sets and in quantum sets are compatible. Moreover, the Yoneda embedding composed with a linearization functor provides the embedding of the category of sets into the category of quantum sets, which, moreover, is a symmetric partial model for embedding. Okay, so this means that all these questions about Cartesian product of sets can be embedded into the questions of these monoidal structures of quantum sets. Moreover, this category is equipped with something which is a kind of universal von Neumann algebra. It's a functor which associates with every coalgebra C that it's dual coalgebra, it's dual convolution algebra. And then we have the following theorem. This internal quantum function algebra F is partial commutative in the sense of above symmetric monoidal structure, which means that we have some kind of multiplication which is partially defined on this partial tensor product in this monoidal category, taking values in F. Okay? And we have also a theorem that the image, for instance, of a set under the above embedding of sets into quantum sets consists of a quantum complete set of orthogonal idempotents as above. So previously we defined this quantum set of complete sets of orthogonal idempotents, and now we see that they play a role on the right-hand side to characterize the image of this Yoneda embedding composed with this linearization of sets into quantum sets. So this operation will be called quantization. Having something defined on the level of sets, we can transport this notion to the category of quantum sets, and all structural diagrams in the category of sets which involve Cartesian product can be transported to corresponding diagrams in the category of quantum sets. Okay? For instance, the Birkhoff von Neumann quantum propositional calculus, which is sometimes is called quantum logic of Birkhoff von Neumann, is the result of the embedding of the subobject classifier omega from the set theory into the category of quantum sets. And then this quantized version of these subobject classifiers consists of universal set of idempotents in the images of this universal quantum function algebra, which is this universal kind of algebraic version of von Neumann algebra. Okay. Moreover, we can speak in this language about quantum states. So the set of states is a functor which is applied to a given coalgebra, provides an affine space of elements of this coalgebra, satisfying the condition that the counit in this coalgebra evaluated on this element is equal to 1. In this way, obtain a affine space of affine functions on the set of states, and this space of affine functions now becomes a contravariant functor, which means a presheaf on the category of coalgebras, and we call it a space of expectations on this state of space, space of states of the coalgebra C. And then we obtain something which is called the internal affine space in this category of quantum sets. And now it's a very important construction because it's fundamental in quantum theory, but it's not representable by any coalgebra. And this is the main reason why representable quantum sets alone are not sufficient for quantum theory. So we need this machinery of quantum sets, maybe not representable ones. Moreover, in this language, we can speak about expected values. To define an expected value of an observable in a given quantum quantum state, we can apply a canonical, even natural functor from algebras to some universal space of functionals. It's in fact, tautological linear map of internal F1 spaces, which associates with every observable, which is an element of this universal function algebra, which is associating a number, which will be called the expected value. Okay. Also, associative algebras can be regarded as some objects which can be described by quantum sets. Namely, every coalgebra can be associated with its construction of a co-free coalgebra due to Swidler. And this co-free coalgebra represents a pressure on coalgebras of the following form. The value of this pressure is simply equal to the convolution algebra with values in this algebra A itself. In this way, we obtain an object of some category in which morphisms are defined below. Morphisms in this category are morphisms in the category of so-called monads over, algebras over a monad of the form which associate with every algebra A, this convolution algebra taking values in this algebra. It turns out that this construction is a monad, and every monad admits its category of algebras. And these algebras of this monad are simply these convolution algebras of this coalgebra C taking values in these algebras. For instance, on the right-hand side of this equality is A prime and A. And then it turns out then the quantum set of elements or C elements of this quantum set of morphism between these quantized algebras is nothing more but the quantum set represented by the construction introduced by Swidler under the name of the measuring coalgebra between two algebras. Okay, so now having explained this structure of the category of quantum sets, we can ask what should be counterparts of many constructions which use sets as building blocks. The first such a construction, which is interesting, is the situation of quivers. So a quiver is the structure got by forgetting the composition law and units in a given category, and was introduced by Pierre Gabriel, who was interested in irreducible representations. And he reduced problems about irreducible representations to problems of quivers. And the definition is that a representation of a quiver is a functor from its path category to the category of vector spaces. So you can speak about path category of a quiver, since every quiver is generated by arrows, and these arrows can be concatenated. In this way, you obtain a construction that gives for every quiver a category, a free category generated by this quiver. And representations of these quivers are simply these functors from this category of paths to the category of vector spaces. It's a famous construction in mathematics because Gabriel proved that connected quivers with a finite number of intercomposable quiver representations over an algebraic closed field are precisely the Dynkin quivers. This means quivers whose underlying undirected graph is a Dynkin diagram of the ADE series. Moreover, the intercomposable quiver representations in this case are in bijection with the positive roots in the root system of the Dynkin diagram. Okay? It means that representation theory of quivers is, in this case, when classification of representations makes sense, is the simplest, deeply meaningful combinatorics encoded by these Dynkin diagrams. Okay? So now the idea of exploiting the fact that quiver is in fact some proto-algebraic structure consists in associating with a given quiver some algebraic invariants, some functorially associated, for instance, algebras, and then associating with these algebras some further invariants of these algebras. These algebras, which are important in our context, are algebras which are defined in terms of paths of a given quiver. For instance, with every path algebra, by linearization of the corresponding path category, we obtain the algebra of paths, which is called path algebra. If we divide this path algebra by some relations, which are written below, we obtain something which is called the cone-path algebra. And the further quotient of this by the complete system of conditions below defines some algebras which are called Leavitt path algebras. And these algebras are very important and interesting, first of all, because modules of this over these path algebras are very interesting. For instance, path algebras have modules, and for path algebras, these modules are nothing else but representation of quivers. Again, for Leavitt path algebras, modules are quite unexpected properties, making them very interesting. For instance, finitely generated free modules in general do not have invariant rank, which is the result, celebrated result due to Leavitt. Moreover, some of them admit non-simple modules whose endomorphism rings are fields. This is a result of due to Preußer, who generalized the construction of Gonsalves and Roy. These are very unexpected properties of this canonically associated with Quivers algebras. And now, what is the merit of this algebraization of quivers? The merit is that parallelism between combinatorial properties of a quiver and algebraic properties of its Leavitt path algebras. For instance, if you are interested in details, you can find them in lecture notes of Jean Abrams, giving a mini course on Leavitt path algebra in Floripa on March 2017. You can find it on the internet. However, besides this very nice parallelism between combinatorics and algebra, the conceptual picture behind many phenomena of related to module theory of this path algebras is still to be unraveled. So the main problem is the problem of functoriality. For pure path algebras, the problem is obvious, it's immediate. But for other type algebras, the problem is really very difficult, especially when one expects the functor to preserve or dualize some special structures, like, for instance, push-outs, where these problems were considered by Quivers, Hayes, and Tobolsky. First of all, morphism between Quivers have to be modified. The condition CK2, the second Kunz-Krüger relation, depending on regular vertices, is very complicated. Moreover, algebras, despite having an explicit presentation in terms of quiver, are linear objects, and therefore it's hard to control their functoriality in terms of the combinatorics alone. Okay? So what's the goal and what is the strategy in this situation? So now our goal is to unravel the categorical backbone of this construction, and this will explain many features which we are interested in. So first of all, this construction, this way of explaining this parallelism between combinatorics and this algebra uses a resolution of singularities of a quiver. Thanks to this, we can avoid difficulty with singular vertices for some price. This price is that we do not speak now on algebras up to isomorphism. We can speak about them only up to Morita equivalences. Second, this describes the module category of Leavitt-Path algebra up to equivalence, and it is linearized from the scratch. Because of the last feature of our construction, this works even for quantum quivers. About resolution singularities, we have two theorems. First theorem, due to Drinan and Tom Ford, says that every quiver with countable many vertices can be desingularized by adding tails to sinks and infinite emitters, making all vertices in this graph regular. Moreover,
wait, TOMASZ, sorry. How?
Yes.
So first, for starters, when you say tails, do you mean like infinite tails going backward?
Yes, there are tails and some other constructions using tails. Okay.
But I don't understand how putting a tail to an infinite emitter would stop it from being an infinite emitter. It completely doesn't make sense to me.
No. This is not only adding tails. There is some special construction based on adding tails, but which is more complicated. And it was
because it's not what you wrote. You said by adding tails to sinks and infinite emitters. And I understand that, adding tails to to sinks maybe, but wait a second. So imagine we have a sink, okay? So when you add a tail, so you make this a sink an emitter of a tail. Do I understand you correctly? Let's take a sink. So how do I add a tail to a sink? So it's no longer a sink. It just emits the tail. That's what you mean.
Of course, if you add simply tail to a sink, it's not a sink anymore.
Yeah.
No more. Okay.
Well, it depends what you mean by adding tail.
But killing.
I'm asking what it means to add a tail.
Tail is a concatenation of infinite number of edges.
That I understand, but what you mean by adding it to a vertex? You add it from behind or from above. Do you start with tail or do you end with tail there?
No. They are tails which are emitted from this.
Say it again. What?
They are emitted.
Emitted, right? So this tail is emitted.
So they. Yes. Otherwise, if you added them in a different way.
So why is it called a tail?
It is, I'm not responsible for this. For that, this is a theorem of Drin and Tom Ford, and it's a theorem of desingularization. Moreover, we have a theorem of Abrams and Aranda-Pino that every Leavitt path algebra is Morita equivalent to the Leavitt path algebra of a regular quiver. So thanks to the first theorem, we can remove these singularities. We can replace our quiver by a regular quiver, and moreover, we can do this in such a way that the resulting Leavitt path algebra will be Morita equivalent to the Leavitt path algebra of so desingularized quiver.
Okay.
So this means these two important theorems allow us to focus on regular quivers. However, then we can speak only about Morita equivalence class of the resulting Leavitt path algebra, or only about the category of modules over this Leavitt path algebra.
And when you say regular quiver, you simply mean that every vertex is regular.
Yes. Okay, so now, according to the ideas from the first part of the talk, if we have a notion of a quiver, we can replace the diagram consisting of the source map and the target map by diagrams in the category of quantum sets, with a small modification when we speak about vertices and some kind of opposite vertices, which modification is responsible for passing from the coalgebra to the opposite coalgebra. You remember that now, talking about quantum anything, we do not assume that our coalgebras are co-commutative. Therefore, these opposite vertices could be of different sort than simply vertices. And then there is a theory which comes from the theory of quantum categories introduced by Day and Street, Street and John Day. According to the idea of Gabriel, that quiver is a category with composition and units forgotten, we can take the definition of Day and Street of this quantum category and forget about composition and units. And then we obtain something which was introduced by Chikladze under the name of quantum quiver. Okay? And the resulting construction can be put into the machinery of quantum sets, and in this way we obtain the category of representable quantum sets. Representable quantum quivers. And if we replace these representable quantum quivers by arbitrary presheaves on the category of coalgebras, satisfying formal properties of these representable ones, then we obtain the formal notion of quantum quivers, not necessarily representable. Okay, and structurally, everything can be written in terms of some maps of coalgebras, mimicking the source map and the target map. Now, they are implemented by homomorphisms of coalgebras in this representable case. And everything can be very easily extended to the case of arbitrary quantum quivers. For instance, the source and target, quantum source and quantum target analogs of classical notions, where the pair of the source and target takes values in this partially defined kind of Cartesian map of quantum sets. Okay. And then to relate these constructions, we need some generalization of mappings, relations, and classical correspondences between sets. So quantum correspondences are defined as follows. So if we have any representable quantum set, let's say X, then we can associate with it the category opposite to the category of right comodules of this coalgebra representing this representable quantum set. If we have a morphism of these quantum sets, which means this natural transformation of representable functors, which is tantamount to some coalgebra map, then we can associate with such a morphism a pair of adjoint functors between such obtained opposite categories of comodules. And these functors are described as follows. So one is the co-restriction functor, defined by the following composition. And this functor has a left adjoint, which is called the co-induction functor, denoted by F upper star, which is defined in terms of something which is called the cotensor product, introduced by Moore. And we say that the morphism of quantum sets is discrete if there is an adjunction. This left adjoint functor F upper star admits a left adjoint, which is called F lower shriek. And classical mathematics is full of this construction. For instance, if we have classical set, then the category Cx is nothing more than the opposite category of vector spaces with a decomposition into direct sum parametrized by elements of a given set. Okay? If we have a mapping, a usual set theoretical mapping between two sets S and T, this is, first of all, equivalent to a coalgebra map between linearizations. Okay? And with this, we have a pair of adjoint functors, even a triple of adjoint functors of the following sort. F lower shriek is the following product. F upper star is simply some theoretical pullback of direct summons of this sum, and F lower star is very similar to this F shriek, but this time the product is replaced by this direct sum, which means that only finite sums are allowed. Okay? Something is happening. Okay. And then we say that such a morphism of quantum sets in general is called quasi-finite if these two functors, F lower shriek and this F lower star, are equal one to each other, which means that this pair F lower star and F upper star form a Frobenius pair of functors. In the classical situation, this Frobenius pair corresponds to the fact that the statistical map between sets has finite fibers, nothing more. In this quantum case, there are interesting analogs of this property, which are given by the fact that there is some functor which is called Coulomb, which was introduced by Swidler, and properties of this Coulomb as adjoint compared with the properties of the cotensor construction allows us to define corresponding left adjoint to this f lower star, this functor f lower shriek, and formulate the property of being Frobenius, which is a kind of quasi-finiteness in quantum non-commutative case. Okay. Oh, sorry, something too much. Okay, so now having these quantum sets related by this adjoint pairs of functors between opposite categories of commodule categories, we can define quantum correspondences between quantum sets. So by definitions, they are morphisms of representable quantum sets of the following form: from a given one set representing this correspondence to this kind of partial Cartesian product of this set Y and opposite set X0. And we call corresponding pairs of morphisms from F to Y and from F to X0 source and target, or quantum source and quantum target morphisms respectively, and we denote them as classically by S and T respectively. Okay? And then with such a situation, we can associate some algebraic construction. This is called the Kunz-Pimsner-Morad. If we have an adjunction between two endofunctors, Q upper star and Q lower star, on some category C, then we have something which is called the unit and the counit of this adjunction. There are some natural transformations, the unit from the identity functor to the composition Q lower star, Q upper star, and the counit from the composition Q upper star, Q lower star to the identity endofunctor. And then we can associate with such an adjunction between two endofunctors some category which we denote by ST of Q, and we call it stable category. Objects of this category are objects of the category C being equipped with a retraction of the direct image Q lower star of N onto this object N, inducing a retraction of the value of the composition of these two functors, Q upper star, Q lower star, on this object N, onto the value of Q upper star applied to N, leaving the counit of the adjunction stable. It's a complicated condition which can be a little bit easier written algebraically, but at the moment, for the purpose of the definition, it is important that morphisms in this category are morphisms in this category C, preserving this retraction. Algebraically, these objects can be written as objects N equipped with two morphisms, omega N and sigma N, which apply to this functor N and this Q lower star N satisfy the following identities. So these are algebraic identities. Okay. For the morphisms, some obvious compatibilities with this structure is required. Okay? And then we have the definition. We define the Kunz-Pimsner monad of this adjunction as being the quotient of the free monad generated by the coproduct of these both adjoint functors, endofunctors, Q upper star and Q lower star, by the congruence generated by the following system of identities. So this system of identities use the unit of the adjunction, co-unit of the adjunction, this structural natural transformation, this maps sigma n and alpha n, and this application of Q lower star and upper star to corresponding structural morphisms. Okay? And then we have the following example. If we apply this formal construction to the situation when this pair of adjoint functors is implemented by tensoring with a finite generated projective module and its dual, then as a result, we obtain the following construction. This Kunz-Pimsner monad is equivalent to a monad implemented by the following construction. It's a tensoring by a B bimodule, which is a quotient of the tensor algebra generated by this finite generated projective module together in the direct sum with its dual by the following canonical relations, which use only the unit and the co-unit of this adjunction. And these unit and the co-unit, by the way, in this case, are simply the dual basis in the evaluation map, respectively. They are very concrete. Okay? And then we have the following theorem. The Kunz-Pimsner monad of the adjunction defined as above by a finite generated projective from the right, B module P, is isomorphic to the tensoring over B with the Kunz-Pimsner B ring OP. And in the opposite direction,
sorry, can you remind us what is Kunz-Pimsner B ring OP?
This is this construction. It's a quotient of the tensor algebra of this direct sum divided by canonical relations.
Okay.
Pure algebra. So the theorem, first theorem, says that previously introduced abstract Kunz-Pimsner monad, okay, is equivalent with the endofunctor of tensoring with this Kunz-Pimsner ring. Okay? In the opposite direction, as every monad has its category of algebras, which is called the Eilenburg category, the Eilenburg category, which is a quite abstract notion, now can be characterized in the case of the Kunz-Pimsner monad implemented by tensoring with this Kunz-Pimsner B ring, OP, as follows. It is the same as the stable category of this adjunction. So we are coming back to this adjunction and the stable category of adjunction. Okay? This Eilenburg category. If we have the question about this Eilenburg category, we can forget some part of the structure and ask if this forgetful functor is monadic. In this situation, the second theorem says, the second part of the second theorem says that forgetting the retraction which was the part of the definition of the stable category, is a functor which is monadic, and monadic functors can be reconstructed by an appropriate monad. And in this case, the resulting monad is again the Kunz-Pimsner monad. So this means that these stable categories of this adjunction, first of all, they are tantamount to the structure of the Kunz-Pimsner monad. And this Kunz-Pimsner monad in this purely algebraic situation are nothing but the monad implemented by the Kunz-Pimsner ring. Okay, so now we get to our main construction, which is called the Leavitt path monad of a regular quantum quiver. So we say that a representable quantum quiver is called regular if this S upper star, this inverse image functor related to this source morphism, is faithful and is Frobenius. If you think about classical situation, this is equivalent to the situation that fibers of S are finite, okay, which means that all vertices are finite emitters.
Mm-hmm.
And the property of this functor of being faithful means that S is surjective, which means that there are no sinks.
Mm-hmm.
Okay? So this is some abstract.
And how about Frobenius? What does it mean? What does it mean, Frobenius, in this context? I mean, what does...
Frobenius means precisely finiteness. Finiteness of fibers.
Oh, okay, okay, yeah, okay, yeah. Mm-hmm.
Okay.
Mm-hmm.
Okay. So in the classical case, of course, it makes sense in general. And
so wait, now when you talk with representable quantum quiver, to put it very succinctly, so now your E and V are coalgebras, right?
Implemented by coalgebras. Yes.
They're implemented by coalgebras, and you have this.
And S and T are implemented by coalgebra maps.
Okay. Mm-hmm.
Okay. And then, in this situation, with every representable quantum quiver, we can associate an adjunction Q upper star left adjoint to Q lower star. It is defined by this regularity condition applied to the pair of functors S shriek, lower shriek, and S upper star, and T upper star and T lower star. Okay. Namely, Q lower star, this right adjoint, is the composition of T lower star and S upper star, and Q upper star is the composition as lower shriek with T upper star. And then by this regularity condition, you can easily check that you have some adjunctions satisfied, like S lower shriek is left adjoint S upper shriek, and so on. And as a result, this Q upper star is left adjoint to Q lower star. And then we are in the situation when we can speak about Kunz-Pimsner monads associated with this adjunction. And this Kunz-Pimsner monad in this situation, defined by this representable quantum regular quiver, is called the Leavitt path monad of this regular quantum quiver. So first, an example. What happens in our previous algebraic situation, where we have an algebra B, and we have finite generated module, which is a bimodule over B, and then we have some regular quiver. Then with this quiver, we can associate, first of all, a bimodule P spanned by elements PE corresponding to edges and elements.
Wait, so now your quiver is classical, right?
Yes, it's completely classical. So having edges, we can span this finite generated projective module P, which is a bimodule, having orthogonal idempotents spanning this algebra B. We can define an action of this generators of this P, action of this orthogonal idempotent on these generators of this module P from the left and from the right.
Yes.
And the recipe is very simple. And such a recipe we call the algebraic autocorrespondence defined by regular quiver. And then it turns out that for every regular quiver, classical quiver, the Kunz-Pfimster monad of the algebraic autocorrespondence defined by the quiver is isomorphic to the tensor ring over B with the Leavitt path algebra of that quiver. Leavitt path algebra in the classical sense. Right? So first of all, this relates our construction of our Kunz-Pfimster monad in the case of a monad of an adjunction coming from the regular quiver with this Kunz-Pfimster ring. Next, this Kunz-Pfimster ring becomes this Leavitt path algebra of that quiver. And finally, the stable category of this Kunz-Pfimster monad is the category of representations of that quiver satisfying some additional property. So this additional property makes objects of the stable category not only representations of this quiver, but makes these representations equipped with some kind of wrong way map, which is a kind of how to say, some averaging against a map. And such representations of a quiver equipped with such averaging we call stable representations of this quiver. So it turns out that for a given quiver, the category of stable representations is precisely the category, the Eilenberg-Moore category associated with the the path-Leavitt monad associated with this regular quiver. And this also is true in this quantum situation. The following theorem relates all these notions together. First of all, the Eilenberg-Moore category of the Leavitt path monad of a quantum quiver is canonically equivalent to the category of stable representation of that quiver. And conversely, forgetting about arrows in a stable representation of the quiver is monadic, and the resulting monad is the Leavitt path monad. In particular, in this purely algebraic case, it is tantamount to the usual Leavitt path algebra. So it is, in a sense, some deep categorical explanation of this categorical backbone of Leavitt path algebras. So having done with this construction, one important question arises. How functorial is this Kunz-Pimsner monad with respect to this adjunction, defining this Kunz-Pimsner monad? And second, how much functorial is the dependence of the corresponding Leavitt path monad on a corresponding regular quantum graph or quiver. So first of all, since everything depends on this Kunz-Pimsner monad, the first answer on functoriality of this Kunz-Pimsner monad says that it is functorial under the correspondences intertwining Q adjunctions. This means that these are correspondences F. You remember, the correspondence is, in fact, in this case, a pair of adjoint functors, F upper star and lower star. And we say that this correspondence intertwines Q adjunctions if F upper star, Q upper star is related by some natural isomorphism with a composition Q prime upper star with F lower star. These two adjunctions are intertwined in this sense. This is tantamount to the similar adjunctions in the opposite order composition in the opposite order of adjunctions when you replace not only the order of this composition of these symbols with upper stars by the opposite composition of the same symbols with lower stars, but you have also to change the direction of this isomorphism.
Okay, Tomek, two things. One is that you're all over time. And second, I mean, for crying out loud, Kunz spells with a T. C-U-N-T-Z.
Oh, sorry.
How can you butcher such a famous name?
Yeah. Sorry, Joachim.
Yeah. Okay. So please try to wind it up.
Okay. So the following theorem subsumes the functoriality of the Leavitt path monad. So this functoriality of the Kunz-Pimsner construction specializes to the following fact. So first of all, the Leavitt path monad is functorial with respect to correspondence satisfying two conditions. First one says that intertwining this is a factor intertwining the source functors, so similar as is above, but now we have instead of Q upper star and Q prime upper star, we have now two different F upper star. One is related to set of edges or quantum set of edges. Another one is related to quantum set of vertices. Second intertwining property is about this target functor. But this target functor must satisfy another condition, which is called Beck-Chevalier condition. Okay? So this Beck-Chevalier condition in category theory is a very frequent condition in the situation when you are speaking about pullbacks.
Yeah.
So you can think about this condition as a kind of generalized pullback in the situation where everything is defined in terms of maps between sets. Okay?
So Tomek, if you remember our discussion, so this is what would correspond in the usual setting of Leavitt-Path algebras to this target bijectivity condition, right?
Yes.
Okay,
Your target bijectivity condition is on the nose, the pullback property associated with the target maps and these maps between vertices and edges.
Yeah, because it's a very fundamental thing when you go beyond just talking of subgraphs. If you walk this way of Katsura and what we did in the discrete topology, then the condition taking care of a first constrictor relation, allowing you to induce a homomorphism of algebras or star homomorphisms of sister algebras, is precisely the targeted bijectivity condition, which, if you want, says that if you look at a natural commutative diagram for the target map, it must be a pullback diagram. And that's a very fundamental condition which gives us the functoriality. So in the contravariant, I'm extremely happy that it has such categorical incarnation or presentation.
So it is not only categorical incarnation in the case of classical Quivers directed graphs. It's a natural extension to the realm of quantum graphs. Quantum Quivers. Sorry. So this is essentially the last page.
Okay.
So
thank you so much.
Yeah, thank you very much.
Okay, so let me ask you some immediate questions before I ask the audience for questions. Could you go back to something more than thank you? When I look at this Leavitt-Path monad, so I'm a bit confused. Do you have, at the end of the day, I have some quantum quiver, let it be representable, let it be regular, assume whatever you will. But then out of this quantum quiver, do you get an algebra or just a monad? This is what confuses me. Do you have a Leavitt-Path quantum monad?
In general, it is a monad, but in algebraic situation, this monad is represented by an algebra.
Okay.
It's implemented maybe in this way.
Okay.
Would be better.
Okay.
And algebra, in fact, is a shadow of something living in category theory. If you feed this abstract nonsense with the algebraic context, this produces you algebra.
And it will be an algebra which is produced for a quantum quiver. It doesn't have to be classical quiver.
Yes.
Okay. So you can now guess my second question. I would like to have some nice, natural, interesting example of a quantum quiver which is not classical, producing for me this Leavitt-Path algebra of a quantum quiver.
Natural examples. Okay. There are some, of course, very easy but degenerate cases. Probably are not interested in. But anyway, they are non-trivial. For instance, when both arrows T and S are equal, okay, then you have only loops. Then you have some non-classical loops constructions which could be put into this framework. Some other examples come from the situation when you have interesting quantum categories. Okay? Which are, for instance, quantizations of some classical categories. So if you quantize some classical category, for instance, if you forget about commutativity and then you deform it under some formal one parameter deformations, you can obtain some bialgebroids. And there are interesting examples. In every bialgebroid, which corresponds to some, let's say, quantum category, you can forget about composition. And then you obtain a non-trivial quantum quiver. And then ask, what is its Leavitt path algebra, or Leavitt path monad.
Okay, in the same vein, imagine now that I take my ground field to be the field of complex numbers.
Yes.
Imagine that I introduce a natural some star structure. Can I have like the graph sister algebra now, or quantum graph sister algebra, quantum quiver sister algebra? Do you have a say?
I don't know no, I don't know. I don't know, because if you have graph encoding the structure of this Leavitt path algebra, then you have a set of generators and relations.
Yeah.
You don't have anything like that if your quiver is quantum. Because except of quantum elements, except of classical elements, which could generate something like a Leavitt path algebra, you have some non-classical. You have some quantum set of elements, non-classical elements, which cannot label generators of a usual Leavitt path algebra. Okay, because generators of usual Leavitt path algebras are labeled by elements of sets, classical sets of vertices and edges. Now you do not have these sets. So this kind of presentation is impossible.
Yeah, okay. So I see a problem, right? I see a problem. But you still have an algebra, right? So it's natural to see
you can have
algebra,
yes,
and say that I can make it in a natural way a star algebra, then I can always ask a question: what is the universal enveloping sister algebra, such an algebra? Does it exist to begin with? And it exists, what is it? So that's my question. Okay, how about K theory?
So you can. I don't know.
Okay.
I don't know. So I don't know anything about K theory, because this recipe of computing K theory of Leavitt path algebras is also based on sets, in particular on adjacency matrices. Okay.
Yes.
So now we don't have anything like adjacency matrices, not even in the sense of quantum graphs. It is something much more complicated. It is not enough to have to put operators into as entries of this matrix, because this matrix is not defined. There are no positions in this matrix to be filled by operators to define a quantum graph, for instance, quantum adjacency matrix. But now this is not even a matrix. This is something maybe if somebody invents something like quantum matrices, maybe this could be used to solve this problem. But I have no idea what could be these quantum matrices yet.
So let me ask my last question. So does this point of view of embedding the usual ordinary classical quiver Leavitt-Path algebras into this quantum context, does this point of view allow us to, this new point of view, allow us to solve some problems within Leavitt-Path algebras? Because often, when you look at a given structure from a completely new and different point of view, things are now aligned differently, and what you didn't know how to solve, now you know how to solve. So would you have an example of some internal issue of classical Leavitt-Path algebras on which people were stuck because they're looking at it classically, but now we have your quantum perspective on it, and it's a completely new perspective, and now with this new point of view, new perspective, we know how to solve these problems in classical Leavitt-Path algebras.
Okay, so even in the classical situation, maybe it's not the solution of some conjecture previously posed by anybody, but it's quite unexpected that it's a relation between category of representations of the Leavitt-Path algebra and this category of quiver representations.
This I agree, yes.
Satisfying some additional property. Okay? Because of course we know this parallelism between combinatorics of a directed graph and algebraic properties of this Leavitt-Path algebra. However, of course, these algebraic properties have its shadow in the representation theory of this algebra. And then the correspondence between the representations of a defining directed graph and properties of the representation of this related Leavitt-Path algebra is some kind of explanation to some extent of this parallelism between this combinatorics and this algebra, which was the main problem which I posed when I started developing this approach.
Yeah, I like it. Yeah, I understand. Okay, so that's it from me. Any questions? You have any questions? Anybody from the Zoom? Adam?
Yes.
Santiago?
Yes. I would like to ask one question. So could you go back to the slide when you described how Birkhoff von Neumann logic arises as in this process of quantization of this classical subobject classifier? Yes, just the two elements set. And yeah, exactly.
Yeah.
And okay, so is it something similar regarding the so-called POVM, positive operator valued measures? Could you get this POVM by this process? It would be interesting.
I don't know. It is not about measures. So look, this part, Birkhoff von Neumann quantum propositional calculus, is a structure of idempotence in the von Neumann algebra.
I see. So maybe like positive operators.
So they are, yes. So they are rather observables. And measures are like states, rather. So the next theorem is about this. Maybe not theorem.
Okay, I will withdraw my original version of my question and let me reformulate it. Instead of projections, could you get positive operators in this construction?
Yeah. So everything. If you take the ground field equal to complex numbers, you can speak about positivity. If you intersect all these conditions, which are pure algebraic, it's pure algebra, with positivity, then you obtain here self-adjoint projections. Okay? So these self-adjoint projections in this von Neumann algebra is nothing but quantized, in my sense, truth and false values of the
Yes, but
internal logic.
I'm thinking about something in the spirit of the so-called fuzzy logic, you see. So projections.
No, it's not fuzzy. No, it's not fuzzy. It's precisely as
Neumann, TOMASZ, Birkhoff von Neumann is not fuzzy. Exactly, it's non-commutative.
Yes, yes.
Non-Boolean, but not fuzzy. But the positive operators are a non-commutative analog of fuzzy logic, of fuzzy classical logic, if you could call it like that.
You mean know. Okay. So you mean convex combinations of projections?
In general, even more general, just positive operators. Maybe positive, but also smaller
from
or
algebraic
equal than identity.
From algebraic, but from algebraic point of view, up to closure, okay. So all positive operators are closures of are limits of these convex combinations of projections.
Okay, yeah, you are right.
Okay. So by your fuzziness, you mean simply this closure of convex combinations.
Yes, but for example, I'm thinking about taking a unit interval, if it is allowed, I don't know, and then taking the quantized version of a classical unit interval, and then maybe obtaining all positive operators smaller or equal than identity. Does it work like that, or?
I don't know.
Okay.
But if you want to combine it with measures, then look at next construction, okay? Space of expectations. So these affine functions on the space.
I see. But
these are like measures.
Yes. But TOMASZ, this positive operator valued measures is more like some generalized notion of observable. It is not on the level, on the side of the states. It's the decomposition of identity, and projective measurements are thought as also the composition of identity, but in such a way that all ingredients of this decomposition consist from projections, and positive operator valued measures are more general, but okay, this is not on the side of state. There is in fact a duality between observables and states, and the positive operator valued measure, it should be thought as a generalization of observables, not of states. Okay. Okay, thank you.
Yeah, so in the spirit is the same, but I'm not applying this. Of course, inside of this f of c, which is a purely algebraic counterpart of a von Neumann algebra. Because what is a von Neumann algebra? Von Neumann algebra is a sister algebra with a predual. So if you forget about functional analysis, it's simply a convolution algebra of some coalgebra. Okay, which is appearing here on the right-hand side of this construction. And observables are simply self-adjoint elements of this. Positive are those which are positive with respect to some positivity. Okay, so it's easy to make these notions inside this framework.
Mhm.
But
Okay,
of
thank
course, you need some functional analytic versions first, and
Mhm.
you have this positivity, which is missing from this approach. But this can be completed in these both senses. The completion with respect to this positivity and this closure with respect to this functional analytic sense.
Okay, thank you.
Mhm.
Santiago, do you want to ask a question?
I wanted to ask if well, if Adam could repeat the last part of his question, because it sounded interesting, but I didn't quite catch it. So, Adam, could you please
Yeah,
kindly?
it was more like remark, not question.
Right.
If you have an observable, like a self-adjoint operator, then you can consider its spectral decomposition. And
Mhm.
for example, you could take a decomposition of a spectrum into disjoint set, and this gives you a collection of projections which
Yeah.
sum up to identity. And in this sense, you get something which is called projection valued measure. Okay,
Yeah.
these positive valued measures are generalization of this idea, where instead of projections, you take positive operators. So this is
Right.
a collection of positive operators which sum up to identity. And some people think about this construction as some sort of generalization of observables. It corresponds to something which is not a projective measurement, but some sort of fuzzy measurement or maybe non-sharp measurement in quantum mechanics. So people in
Right.
quantum information theory are interested in those notions.
Right. And where did that fit into the framework? Where did you think it could possibly fit in this framework? Just to be sure, because I didn't
So,
quite see the connection, maybe.
so as I understand, TOMASZ explained that maybe you could get these positive operators, yes? But here
Yeah.
you don't get in this construction, you don't get this projection valued measure in the sense of the composition of identity, but only the set of idempotents. So my original question was, as TOMASZ pointed out, maybe not well formulated. So I reformulated it in terms of just positive operators bounded from above by identity.
Yeah.
Right.
So my answer was that this purely algebraic approach has some ramifications, and I know how to define the notion of positivity, for instance, for these things. So if you combine it with positivity, I can speak about projections, not simply idempotents.
Right.
Okay, then
Yeah.
I can speak about convex combinations of them. So if I close my combination, I obtain all positive operators.
Right. Spectral calculus and stuff. Yeah. And okay, that sounds interesting. And could you
I didn't
add?
have time to
Yeah.
explain this business with positivity here, because
Yeah.
I wanted to be purely algebraic, but it's possible also in this setting.
Cool. And could you go to I think it was the next slide. Just just want to read it again. It's mostly that.
So purely algebraic,
Okay.
this state is simply an element of the coalgebra C, on which the counit takes value equal to 1.
Do you have here like a well-defined notion of pureness or something? Like, can you distinguish some special elements that generate the rest in a kind of non-degenerate way?
Okay, so we are coming
Like
back
the pure states in a
to
sister algebra, right?
positivity. Okay, so we are coming back to positivity. Okay, so let me say what's the definition of the positive element C. Okay, it is an element whose on which the multiplication results in the sum of elements of the form Ci star tensor Ci, where star is an antilinear involution on this coalgebra C. So first, I'm defining the involution on this coalgebra. It's very similar to define to defining an involution on an algebra. You have to dualize it simply. Okay. So I know what is involution. Then I know what is a positive element in this space of states.
Right.
Then I can speak about convex combinations. They form a convex space. So in this purely algebraic approach, you see in the first line that is an affine space of elements.
Yeah, you're right. Okay, yes.
But after this positivity business, this becomes a convex set.
Yeah. Okay.
And then you can speak about this
extremal points
vertices,
and stuff.
Yeah, external points for this
Right.
convex
Okay.
set. Yeah.
Okay.
So you have
Well,
a notion of
that's interesting.
purity of a state without Hilbert space. Yeah. According to
that's
Krein
cool.
theorem.
Okay, are we good?
Yeah, I think so. Thanks.
All right. If there are no further questions, I don't see any raised hands. Then let us, muchas gracias, our speaker again. Muchas gracias, senor.
Andre has a question, it seems.
Yes, I wanted to ask.
Andre has a question. Hello. Sorry. Yes, go ahead, Andre.
So I have a question about this part of the talk. Sometimes discrete quantum spaces are called quantum sets. And I'm wondering if the category of discrete quantum spaces might be embedded into your category of quantum sets in some way.
Of course, these coalgebras are not so. Wait. Oh, there is a caveat here. There's a caveat because discrete quantum sets in my approach, they have blocks which are finite. Okay, they are simply finite matrices. You can have probably discrete quantum sets in your sense when your blocks are endomorphisms or bounded operators on some infinite dimensional Hilbert spaces. So they couldn't come from coalgebras by algebraic dualization, but maybe after some von Neumann completion, they could. So your quantum sets, are slightly more general. They are more similar to spaces than sets.
So how about the category of finite dimension C-star algebras? Is the opposite of that going to be embedded?
Of course,
Your category?
for finite dimensional sister algebras, they are linearly dual to my finite dimensional star coalgebras.
And is this going to be a full subcategory?
Could you repeat the last word?
Is this going to be a full subcategory? Are you going to get new morphisms?
Yes, of course, of course,
morphisms?
of course, of course. It's a full subcategory.
Thank you.
Okay, so let me stop recording.